Hello, and welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to look at some results from our axioms. Specifically, we're going to look at Hilbert's axioms, but everything can be done in the SMSG axioms as well, and we're going to be looking at triangle congruences. So let's start with some quick definitions. So the first thing we're going to use is we're going to use line to mean a straight line. Right? So line is one of the things that we used as an undefined term in our axiomatic framework. If you recall, the incidence axiom says that, or one of our incidence axioms, that if I have two distinct points, A and B, there exists a unique line that is incident to both of them. So a unique line that passes through both of them. That line we're going to denote with this notation of AB with this arrow over top of it. Then we're going to talk about line segments. So and quite often I will use segment instead of calling it a line segment. A line segment AB is going to be denoted with this line over the top of it. And that consists of all the points on the line AB that are between A and B or that are equal to either A or B. Right? So this is using the idea of betweenness that we talked about previously. Okay, then for the purpose of this class, we're going to define a triangle as three non-collinear points A, B, and C. And these we're going to call the vertices of the triangle. And just as a little point of language, the singular of vertex, the singular of vertices is vertex. Right? So vertices is the plural, vertex is the singular. And this triangle also has the three sides, which are the line segments AB, BC, and AC. And then we talk about the three angles of our triangle, the angles BAC, ABC, and ACB. And when that's not a source of confusion, we will sometimes write angle A, angle B, and angle C as shorthand for that. So let me make a little remark here. This may or may not match your idea of what a triangle should be. So I'm going to make a remark, which is this excludes degenerate triangles. Right? The definition that we're taking is that they are non-collinear. Now, there's no reason for that. I mean, it's convenient for the statement of our theorems, so we're going to work with that as the definition. If instead you wanted to talk about degenerate triangles, you could extend the theory to make sense out of that. And it's not like the definition of a triangle is entirely forced on us, exactly what it means. But we're going to define this edge case so that degenerate triangles are not triangles. And in case, right, this language of degenerate triangle, what I mean by that is a triangle is degenerate if it consists of 3 points that are on a line. So a squashed triangle, if you will. Okay, let's talk about congruence of triangles. So to make sense out of that, we need to define what we mean by congruence of triangles. So here we say two triangles are congruent if there is a correspondence of vertices, so all three sides and all three angles are congruent under this correspondence. Okay, so that's a little bit wordy, but what we mean is if I have two triangles, let's say I have here, I don't know, ABC, and over here I have triangle let's say XYZ. To talk about a congruence between them, whether they're congruent or not, part of the data of the congruence is a pairing up of the vertices. I need to say, for instance, that A corresponds with X, and B corresponds with Y, and Z corresponds with C. Right, so that's the idea of the data that we need to include in our correspondence, in our congruence between triangles, because the correspondence is part of the data of how we line up the two triangles. And then we will write triangle ABC, and then we'll write this symbol that looks like an equal sign with a tilde on top. That's our congruence symbol. Triangle ABC is congruent to triangle A prime, B prime, C prime. When we write it like that, what we mean is we're pairing off those vertices in the order that they appear in. So A goes with A prime, because that's in the first spot. B goes with B prime, because that's in the second spot. And C goes with C prime, because that's in the third spot. Okay, so now let's talk about side angle side. This is one of the things that we took as an axiom, though it's book 1, proposition 4 in Euclid. Euclid's argument implicitly, or maybe I don't understand it correctly, but when I read it, my interpretation is that he is doing a transformational proof of this proposition, which, if we were to axiomatize, to axiomatize those ideas, we would need to have an axiomatic description of the transformations, which I think is slightly more difficult than the point of view that Hilbert takes. We will revisit these ideas when we talk about transformations in Module 2. But for now, we're taking this as an axiom. So we suppose we have two triangles, A, B, and C. So I have, let's say, A, B, C over here. And I have triangle A prime, B prime, C prime. Then to check congruence, we only actually need, right, the definition of congruence is that the three sides are congruent when we pair them up in this way, and the three angles are congruent when we pair them up in this way. But the axiom says we only need to have three of those things. Right? We only need the angle in A to be congruent to the angle in A prime. Right? That's this last bullet point I have here. And then we need the sides adjacent to that angle to be congruent with each other. So AB should be congruent to A prime, B prime, and AC should be congruent to A prime, C prime. This is a little piece of notation here that we often use in geometry, where we put tick marks to indicate that things are congruent to each other. Right? So here I have one tick mark is congruent to the other one I've labeled with one tick mark. The guy labeled with two tick marks is congruent to the other guy I labeled with two tick marks. And then I have that little single line there at the angle is congruent to the little single line at the other angle. Right? So if I have that, then congruence follows, which means from three identities, three congruences of sides and angles, I get all six. Right? So 3 gives me 6. And that is our axiom. Now this axiom actually has a large amount of consequences. The first of these is the Isosceles Triangle Theorem. This says if a triangle ABC is isosceles in A, so what that means is you have a triangle ABC, and I have that the sides coming out of A are congruent to each other. Right? So the side AB is congruent to the side AC. That's what our hypothesis is. Right? If triangle ABC is isosceles in A, then the opposite angles are congruent. So in other words, that angle is congruent to that angle. So this is the Isosceles Triangle Theorem. Let's go ahead and prove it using a proof. I don't know who's responsible for this proof. When I was Googling around, it looks like maybe Legendre from the late 1700s was the first one who had this proof, but I don't know if it might have been older. Okay, let's write a proof of this theorem. So we start with the hypotheses. Let ABC be isosceles in the vertex A. Right? That's by hypothesis. So from this means that segment AB is congruent to segment AC. Right? This is by definition. And so the triangle's isosceles, hence those segments are congruent. So now we consider an identification between the triangle and itself. So I'm swapping the roles of the vertices A and B. Sorry, not A and B, B and C. And I'm imagining flipping B and C. Now what that means, right, if we notice we have that angle BAC is congruent to angle CAB, right? That's just because it's the same angle. We have segment AB is congruent to segment AC. This is by hypothesis. Or I guess I will call it, I'll put a star up here. Right? It's by observation star that we had previously. And we also have that AC is congruent to AB. Again, that's the same statement star, just reversed. And I guess implicitly in this, we've used the axiom of the fact that congruence is an equivalence relation. And then from this, we have therefore used side angle side to show that triangle ABC is congruent to triangle ACB. Right, so we use side angle side on the triangle with itself, but where identification of the vertices has changed. And now what we do is we now use the definition of congruence of triangles to say that we have congruent angles. Right, so the definition of congruence was that the angles in the corresponding spots were the same. So in particular, the angle in B is congruent to the angle in C. And that's precisely what we wanted to prove. So this is a slick trick that uses an interpretation of the identification of vertices in order to use side angle side from my triangle to the exact same triangle. So it's conceptually difficult, but completely straightforward as a proof. So that's, I think, a pretty sneaky proof. I like it very much. And but it's one that you need to spend some time digesting what exactly is going on in here. Okay, so the next little thing we're going to squeeze in here using the side angle side theorem is we're going to talk a little bit about perpendicular bisectors. So before we can talk about perpendicular bisectors, we need to talk about perpendiculars. So if I have two lines, L and L prime, I'm going to say that they're perpendicular if they intersect in some point that I'm going to call A. And if I take points on the first line, so let's draw a picture here so this is clearer. I have a line L, I have a line L prime, they intersect in A, and I want points B and B prime on L so that they're on opposite sides from A. I made them look like they were the same distance from A. That's not required. I just need them to be on opposite sides of A. And then I want a point C on L prime that's not equal to A. So I put C over there. And what I want is these lines are perpendicular precisely if that angle is congruent to this angle. Right, so that's BAC is the one that I did with the little notch in it, and B prime AC is the angle I did without the notch. So in this sense, we're encoding Euclid's idea, right? If you think about what definition 10 said that a right angle was basically, if you stick two right angles together, you get a straight line, and that any two right angles are the same. Well, that's what we're doing. We're saying two right angles together form a line, and any two of them are going to be congruent to each other. Right, so this is how we're going to define perpendicularity in this Hilbert system. And then now we're going to define the midpoint of a segment. I'm going to say that if AB is a line segment, M is the midpoint of AB, if M is a point of the segment AB, and the segments AM and MB are congruent to each other. Right? A fairly normal definition, but we're not guaranteed that it exists, at least not yet. We need to do some work to show it exists. However, if it exists, it's going to be unique from axiom C1 of Hilbert's axioms. Right? So at the very least, I'm allowed to say that it is the midpoint rather than a midpoint. There's at most one midpoint to a line segment. We'll see in a moment is this precisely one. Okay, and then from this we define a perpendicular bisector. The perpendicular bisector of a segment AB is a line L, so that L is perpendicular to the line AB, and L passes through the midpoint of the line AB. I'm going to walk you through on the homework assignment for this week the proof that the perpendicular bisector exists and is unique. And as a freebie, we're going to get existence of the midpoint. Okay, so let's talk about a couple other triangle congruences that you may know and love from your previous exposure to geometry. We have the angle-side angle congruence. So this is now going to be a theorem. So I have triangles ABC and A prime, B prime, C prime. This theorem asks as hypothesis that the angle in A is congruent to the angle in A prime. The angle in B is congruent to the angle in B prime. And the segment between the two angles should also be congruent. And so I have two angles and the side that's between the two angles. If those are all congruent, then the triangles are actually congruent. So let's go ahead and write down our proof. So the idea of this proof is one I think is a very beautiful idea that's of recurring importance in geometry. So I think this proof is a really important one to understand. Okay, we're going to take our original triangle and we're going to put a new point on it. We're going to put a point here. Let me call this point maybe C prime. Sorry, C double prime. We have a C prime already, so I'm going to call that guy C prime. And I'm going to make it so that this distance from A prime to C prime is the same as the distance from A to C prime. So that's the first step of our construction. So let's let C double prime be on the ray AC. So AC double prime is congruent to A prime C prime. This is possible from the congruence axiom that we have from Hilbert's, I think it's the first congruence axiom. Okay, now that we have this C double prime on our triangle ABC, what we do is we observe by side angle side this gives us that the triangle ABC double prime is congruent to triangle A prime, B prime, C prime. And so I'm going to maybe draw that in. Okay, so that dotted triangle is congruent to A prime, B prime, C prime. Which means that we have now two angles here that are the same. At the angle ABC, right, that's the angle in our original triangle at B, by hypothesis is congruent to angle A prime, B prime, C prime, right? That was our hypothesis. But in turn, that is congruent to the angle ABC double prime. Right, so this one is by hypothesis, and this one is by that previous line. Right, so that's, I'm going to call that star. That's by star. Okay, by the fact that congruence is an equivalence relation, we get that angle ABC is congruent to angle ABC double prime. And now from this, we recall from axiom, so this is C4, the ray is unique that makes that happen. So that means the ray BC equals the ray BC double prime. So in particular, C is on the line, C double prime is on the line BC. However, we know from, by construction, right, we have then that both C and C double prime are at the intersection of AC and BC. The lines can't be the same because for us a triangle is three non-collinear points. The vertices of the triangle cannot be collinear. And from this, it follows then that there's a unique point of intersection, or at most one point of intersection. The first incidence axiom tells us that there's a unique line between 2 points. So if we had 2 points of intersection, actually the line has to be the same line. Okay, so we have at most one intersection of those 2 lines, which means that C equals C double prime, and we're now done. Because this tells us that triangle ABC equals triangle ABC double prime, and that guy's congruent to triangle A prime, B prime, C prime. So now we're done. And that's using, again, the fact that we have these equivalence relations. Okay, so we have a couple of other important congruence theorems. There's the side-side-side congruence theorem. So if I give you 2 triangles, ABC and A prime, B prime, C prime, and I happen to know that the sides are pairwise congruent. Okay, my picture, it's obviously false, but pretend it's true. Pretend that these sides are pairwise congruent. Then the triangles as a whole are congruent. So if I know about the 3 sides, I get, as a freebie, I get all 6, right? I get the 3 sides, but then I then get the 3 angles, right? So far, each of our congruence theorems is knowing 3 facts allows us to get all 6 facts. This theorem is a little bit more delicate to prove, so we're not going to prove it in this video. Instead, I'm going to give a special case of it for you to work through on the homework, and we can. But if you have a problem where you want to use it, you can go ahead and cite it and use it, even though we will not have proved every case of this theorem together in class. But I know you can do it once you've worked through one special case of the theorem. Finally, there's the last of our congruence theorems, which is the angle-angle side congruence. So this says if I have 2 angles that are congruent, pairwise congruent to the second triangle, and the side that follows it that's congruent, then the 2 triangles are congruent. So here I need 2 angles in a row to be congruent, and then the next side is congruent. So hopefully either the formal statement or the picture helps you remember this one, the angle side congruence theorem. We'll save a proof of this one for another time. But again, if there's a problem that you want to use it in, feel free to go ahead and use it. So we have 4 congruence theorems. We have side angle side, which is actually an axiom, not a theorem. We have angle side angle. We have side side side. And we have angle angle side. So the question is, what about other sort of 3-letter arrangements we can make out of A's and S's, right? That's sort of the pattern we're seeing. Well, there are 2 other possibilities. The 2 other possibilities are angle, 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 and angle, side, side. So angle, angle, angle is not going to be a congruence theorem. Actually, many of you pointed this out to me in a previous discussion, that angle, 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 what that gives us is actually similarity for triangles. It does not give us congruence. So we'll talk about this in the 3rd module of our course. Then angle side side is not a congruence theorem. We can construct examples of 2 triangles that have corresponding angles, angle side side, and that result, you can end up with these 2 non-congruent triangles with that property. And it is what it is. However, if the angle happens to be a right angle, then it's a theorem. Then you have congruence. So if you have right angle side side, then you have a congruence of right triangles. So that's an exercise. We'll maybe save that for later. But the fact that angle side side fails to give you a congruence theorem is something I'll have you work through on the homework as well. Okay, so happy mathing. I hope you enjoyed the video. Take a look at the axiom handout on Blackboard and take a look at the homework where you work through some of these ideas. See you on the next one.